Hi. So in this video, we're going to be continuing with simple harmonic motion, and this is going to be part 2. Okay. So we're going to be understanding mass spring systems, and based on that, we'll move forward in looking at simple harmonic motion. Okay. So the first thing to look at mass spring systems. Before going there, we can look at the main characteristics of simple harmonic motion, right? So what are the main characteristics of simple harmonic motion? Okay. So the first thing that we look at is that in simple harmonic motion, the period and the amplitude remain constant. Okay. So the period and the amplitude of the oscillation is always going to be staying the same. So let's say that if this is a mass spring system, which we'll be looking at, and let's say we attach it to the wall, then if this mass spring system is oscillating back and forth, then the amplitude of the oscillation and the period of the oscillation is going to be the same. Okay. Then the second thing is that the period is going to be independent. So the period is going to be independent of the amplitude. Okay. So in this case, we can look at this pendulum example, right? Okay, so yeah, and the first thing you just need to know is that the pendulum is not a perfect example of simple harmonic motion. Okay, so it's more of an approximation we use to sort of explain the intuition, but this is not a perfect example of SHM. Okay. So yeah, so with that point, let's look at your pendulum bob over here. So this is a pendulum. We know that you've got your angle to be theta, and then this angle is theta over here as well. Okay, and we also saw that this position over here is your amplitude. Okay, so the amplitude is the maximum displacement from the mean position. So we saw that this is your equilibrium position. So this is equilibria or equilibrium position. And then this is your max in the positive x direction. And then this is your minimum. And this is in the negative x direction. Okay. So what you find over here is that if you create a pendulum bob, right? And let's say that in this case, if you have this oscillation, right? So you would be thinking that if the amplitude is smaller, then the period would be faster, right? If the amplitude is smaller, the period would be faster. But in this case, the amplitude is independent from the period. So the reason is because, let's say if you make the amplitude very high, then the force of gravity acting on this is also going to be much higher, right? Okay. Or in this case, you can think of it in terms of gravitational potential energy, right? Not the force of gravity, the gravitational potential energy. So, if you make the displacement very high, what's going to happen is that you're going to have a higher max height. So all that gravitational potential energy is going to get stored, and then you will convert it to kinetic energy, right? So we'll see that later. So it's more of like, even if you're increasing the amplitude, it has no effect on the period, because in this case, if you increase the amplitude, you just increase the energy, right? You increase the gravitational potential energy, and then your pendulum just starts to move faster and faster. Okay? So you can think of it like sometimes when they demolish those buildings, they use those big cannonballs, for example. So, when you have those sort of big black these circular spherical balls over here, then if you're going to release them from a greater height, they're just going to move faster, right? So therefore, they're going to have a higher gravitational potential energy. So we'll look at that. So the main thing to note over here is that the period is independent of your amplitude. Okay? Period is independent of amplitude, and the amplitude and the period always stay constant in a simple harmonic motion. And this is considering the fact that there is no frictional force. Okay? If there's no frictional force, the period and the amplitude will just stay constant. Okay? So now what we can do is that we can understand these mass spring systems. So let's say that if this is your mass spring system, right? So this is attached to the wall. You've got a spring over here, and then this is your mass. Okay? So we'll say that this is your equilibrium position. Okay? So now what's happening is that, let's say if you have a force acting on the mass, and then let's say if this mass starts to stretch, or the spring starts to stretch, and then this is going to be this position. Okay? So if this is your equilibrium position, then this tends to be your displacement. Okay? So this is your max displacement, or the maximum amplitude. And then similarly, let's say that the mass comes back and then it contracts. So this is a contraction. And then once again, this is going to be your displacement. Okay? So this is your mass spring system. As we can see, there is an oscillation. The spring is going to the right, then it's going back to the left. And then in the final position, what's going to happen is that the spring will go back to its equilibrium. Okay, so once again, this is equilibrium. So if you see this, then what's happening over here is that this mass is first going to the right, then it's going to the left, then it's going to the right. Okay, so it's going to the right, coming back. This is how the oscillation of this mass is happening. Okay? This is how the oscillation is taking place. Now, what we can do is that let's say if this is our axis, right? Think of it this way. So this is your displacement. Okay? And then down here, let's make this as time. So if you see this movement, right? If you see this movement, so we are adding a factor of time. So as the time passes, the displacement goes to the right, then it goes to the left, then it goes to the right. So you see this curve over here. Okay, this is what happens. You get a curve, and the reason you get a curve, so you might be thinking, why do we just not graph displacement like this, right? Why don't we not just make it left and right? But the main thing is that when you get this displacement, you're also adding a factor of time. So that's why you get this curved position. Okay? And there's a pretty good intuition for this. You can think of it in terms of parabolic motion, right? So if you see parabolic motion, you would have remembered the example we start off with, where we say that there's a person over here, and they basically throw a ball in the air, and then the ball in the air goes to its maximum height, and then it falls back down. So this is how we graph its movement, right? We just say that it's going in this up and down position. Okay? So this is how the graph happens, and this is how we sort of analyze the kinematics that's taking place, right? But now, let's say if I introduce another variable, okay? Let's say if I introduce your displacement x. So when you introduce another variable, what's going to happen is that it's going to go up and down like this, but you're going to get this displacement taking place. So let's say that if this is your displacement in the x direction, this is your height in the y direction, then when normally without displacement, it's just up and down, right? But then the moment you add the displacement, it goes to the max height, falls back down. So you get a curve, okay? That's what you get. So it's a similar intuition that we use for simple harmonic motion, okay? In simple harmonic motion, normally if you're not factoring in time, we'll just make it go left and right. But because we're adding time, then you get this sort of curved position, okay? Right? So the mass is going left and right, but with time, you're getting this sort of curve that's taking place. Okay? So in this case, the displacement starts at 0. This is time. it goes to the maximum, comes to 0, goes to minimum, comes back to equilibrium. Okay? So as you can see, this is a sine or cosine curve, right? So for example, let's say that I started off, let's say in this case, because I start off at the equilibrium, I get this curve, right? This is my equilibrium position. But now let's say that I start with this as my equilibrium position, right? So I'll draw another one over here. If I draw another displacement over here, right? And then this is your max displacement. Then what you can see is that in this case, the curve that I would be getting is like this. So it would be sort of like this curve, right? Okay. So if you start off with your displacement, then in this case, over here, the displacement is 0. So this is your starting point. But in the second curve, our displacement is to the right. So we'll make a displacement over here. Then in this case, you can draw this curve and then you get some sort of movement like that. Okay? So the main thing for this is that with these mass spring displacements, the displacement is a function of sine or cosine. Okay? So that's what you would need to understand over here, that the displacement is a function of sine or cosine. Okay? So that's the third main fundamental thing that we need to see over here, is that in this case, what we see is that displacement. So in this case, the displacement, velocity, and then your acceleration, right, they're going to be sine and cosine functions of time. Okay. So these are like the fundamental things that we saw about simple harmonic motion. First is that the period and the amplitude stay constant. Second is that the period is independent of the amplitude. So if you increase the amplitude, you just increase the energy. You increase the gravitational potential energy. So the bob will just move faster. So it's sort of like in this system over here, if you increase the amplitude, let's say if you have a very high amplitude, then obviously the pendulum bob is going to have to go at a higher distance, right? But in this case, you're also increasing its energy, so you're increasing the velocity of this pendulum bob. So even though the distance goes higher, the velocity also goes higher. So we know that the time is just displacement by velocity. So if you're increasing displacement, you're also increasing velocity. So therefore the time, which is your period, is going to stay constant. Okay? So therefore the period is going to be independent of your amplitude. And then the third thing we saw is that in this case, the displacement of velocity and acceleration are going to be sine and cosine functions of time. So the the mass spring system will have this curved motion. And as we have seen, whenever we graph sine curves, for example, you get this curved position. Whenever we draw cosine of curves, then you also get this cosine position over here, right? So in this case, as you can see, we get a cosine curve, right? So that's what displacement and velocity are going to be. They're going to be sine and cosine curves of time. Okay. Now in the next video, we're going to be further analyzing the mass spring system.